Okay, so it is my great pleasure to introduce next speaker, Michele Dall'Arno, and he will talk about the role of SIC structures in the quantum inferential process. So the floor is yours.
Thank you very much. Thank you very much for the introduction. Thank you very much for organizing this wonderful event. And thanks for giving me the opportunity of presenting our results. It's really nice to be here. So I am a quantum information theorist. I am with the Department of Computer Science and Engineering in Toyohashi Daigaku in Japan. And like Philipp said, today I'm going to tell you something about the role of SICs in the inferential process in quantum theory. So just an informal and wavy introduction. Why inference in quantum theory? This is a topic that has been touched in many talks in this. Sorry about my voice, by the way. It has been touched in many presentations during this workshop. So I will just briefly mention the fact that one can claim that there exists a dichotomy between the underlying physical model. So if we believe in quantum theory, like states and effects and channels, quantum instruments, higher order maps, and so on, and what we can access, what an observer can access in a laboratory. And in the simplest situation, what an observer an experimentalist can do is to provide a classical input to the system and read classical output. So press buttons on a keyboard and observe one out of a set of light bulbs lighting up. So these are regarded as inputs and outputs. This is this dichotomy between what can be observed and what the underlying model lies at the heart of the device-dependent approach to quantum information theory. It's called device-dependent exactly because the results that are, the conclusions that are drawn are not based on any assumption on the model describing the devices. Typically, one has just very mild assumptions about, the theory being quantum, or sometimes, like in our case, the dimension of the system that is often called semi-device independent approach because of this assumption. But anyways, we don't think we are in a position to make assumptions about the underlying model describing any specific device. We believe it exists if we believe in the postulates of the theory, but that's about it. So we want to make an inference about such an underlying model. There are many approaches. So I mentioned the device-independent approach, and most famously, there is the so-called self-testing approach. In self-testing, like I'm being a bit hand-wavy now, but one is interested in those situations in which what you observe, so buttons you press and light bulbs that light up, the correlations you observe are so strong that you can pin a single, up to trivialities, up to gauge symmetries, a single specific description for your underlying model. And because of that, self-testing is it's based on Bell violation, so it requires quite a strong setup in many respects. It works only for a limited set of correlations that must violate, as a bare minimum, must violate Bell inequality. Here we are interested in a different scenario. So basically, we want to be able to do inference of any observation that you can make. If the observation is weak, the inference will be weak in a sense that will be clear in a moment. But still, you should be able to do inference no matter what you observe. So the setup we will consider is I will use the formalism of quantum information theory, so the one from like standard textbooks like Nielsen and Chuang, but just to lay down things like a quantum circuit. The quantum circuit that we'll be working on is very simple. It's a box with buttons, and you can press one button at a time and repeat the experiment many times. And this box is connected with another box with light bulbs. And anytime you press a button, you will observe a light bulb lighting up. So now the inference can be about, if we believe in a specific theory, the inference can be about the states that are prepared upon the pressure of each button, or can be about this is a measurement, no? So about the measurement that is implemented, the POVM, if we believe in quantum theory, that is implemented by this box. Both questions, so what should we infer about this box given an observation? So we repeat this many times. Or what we should observe about that box, both are, are legit. But in this presentation, I will mostly focus on the inference of the measurement. And the reason is purely technical, because it's easier, and I'll show you why, mathematically. At the end, I will also mention how to solve the dual problem. And of course, one could think of doing inference of more complicated devices, like these are states and effects, if you are familiar with formalism. There are also transformations of these that are CPTP maps, and transformations of transformations like quantum combs, higher order maps, and so on. But let us start with something very simple. This setup. Okay, I will be using the formalism of GPTs, and there are many reasons for that. Well, the Hilbert space formalism, in my opinion, is very useful because it allows you to treat analytically the characterization of the state space as the set of positive semi-definite operators. So positivity is very easily represented in the formalism in the Hilbert space formalism. Here I wrote like kind of a translation dictionary between the two formalisms. So in the Hilbert space, so I will be working with the formalism to the right. You might be more familiar with the one to the left, or I don't know, maybe not, but maybe you're more familiar with GPTs, I don't know. So operators, so states and effects, are represented by Hermitian matrices in the Hilbert space formalism, and they are represented just by vectors, real vectors in the geometrical formalism. Like a counting argument shows that the degrees of freedom are in number, they are the same. So in building the system, one typically starts from the unit effect, the effect that by definition has probability 1 over any state. So it would be correspond to the measurement with a single light bulb. If I have a single light bulb, doesn't matter what button I press, I will get that, that light bulb will unavoidably light up. And that measurement corresponds to the identity operator in quantum theory, the identity POVM. In our formalism, we will represent it just by an arbitrary vector. I will call it U. I forgot to mention that the dimension of the real space is equal to, I will denote it with L, and it is equal to the square of the Hilbert space dimension. So I think, the degrees of freedom, the number of, a spanning set of the space of operators requires that number of operators. So I will denote it with UL, the unit effect, and it will be convenient. It could be any vector at all. It has no operational meaning what it is, but it will be convenient to regard it as the vector with all entries equal to 1. And the reason is because here we have a duality between the space of states and the space of probabilities. Probability distributions live in a hyperplane orthogonal to the vector with all 1. So this is the space of probability kind of is fixed and in the simplex on that hyperplane. And if we want a very simple to deal with dualism, we can require the same on states. So we say, without loss of generality, we say that in our formalism, the vector, such that the states live in a hyperplane orthogonal to it is the vector of all 1s. So the two states, the space of states and the space of probabilities are basically the same. Then we have normalization. So like I said, states live in a hyperplane orthogonal to the unit effect because they have probability 1 on that effect. And this is translated in the geometrical formalism by that simple condition. So like I said, the inner product of states with the unit effect is 1. So this is giving us the geometry of the situation. So we have measurements, POVMs. POVM satisfy that condition over there. They are the composition of the identity. For those that are maybe not that familiar with this formalism, this just means that if you feed a state into a measurement, the sum of the probabilities of each light bulb to light up is 1. That condition alone does not imply that such probabilities are actually positive, so they are actually positive, they are actually probabilities. And I will drop that requirement, so I will talk about measurement in a sloppy way, requiring that condition, but not the positivity of the effects. Let me justify this. There are several justifications. The first one I could give is, well, when you do tomography, when I've drawn this setup, you probably have thought about tomography. Of course, if you already know the states, you can do tomography of the measurement the other way around. When you do tomography, the easiest thing you can do is a linear inversion. A measurement is a map from states to probability distributions, and being invertible, you can invert it, and given the states and the probabilities, you can get the measurement. That procedure as well drops the positivity constraint. So if you do just a linear inversion, you might end up with something that, a POVM that is not actually a POVM because the elements are not positive. This is a first justification for dropping the positivity condition. Another one is that, well, you can always collect more statistics. If what your inference gives you something that is not positive, it means you didn't have enough statistics. You can get more statistics, get a better inference, and at the end of the day, you will get something positive. Okay, so that condition, that POVM measurements are the compositions of the identity, can be written in the geometrical formalism as the equation to the right. That is the only maybe non-completely trivial thing, but can be seen in a moment. So this is a probability for any state S and any measurement M. This is just a measurement M applied to some state S. And being this a probability, it means that when I take the inner product with the vector of all ones, this is 1. And this is true for any state S. The state space would be denoted with this. So by polar decomposition, this means that this is the unit effect. Okay? So, which is what's written there. This is the unit effect. Okay, so this is maybe the only non-totally trivial thing written in this slide, that the composition of the identity can be written that way. Then we have the inner product. I recall that the inner product only makes sense between states and effects, operational sense. So probably the representation to the right does not actually preserve the inner product between states and states, but I don't care because that is operationally not. The cone of states probably to the right is more widely open or maybe less open, I don't know, than the usual description of quantum, but it doesn't matter because what matters are just inner products of states and effects. And that is represented by the Hilbert-Schmidt product to the left, so the Born rule, and the dot product to the right. So the Born rule, which of course has to be bilinear, because convex combinations of both states and effect has operational meaning. So there is, the Born rule has to be that formula up to linear transformations that are irrelevant because they are just redefinitions of the set of states and effects. Has to be that one. And in the GPT formalism, like I wrote here, the Born rule is just an application of a linear map to a state. A state is a vector. A measurement can be presented as a linear map on it, so a matrix on it. And the output is the probability distribution on the outcomes of that measurement. Okay, just one technicality, I need the final line, so purity. Purity is just what it is, so it's the trace of the squared of the operator, and it is represented by the norm 2 squared in the geometrical formalism. And this will be important because we know that it's true in quantum theory, and it can be made true up to trivial transformations in any GPT, that we have extremal states, so pure states, that live in a ball, in a unit ball. The thing is that for dimensions higher than 2, on that ball, there are operators that are not states as well. So operators that have trace 1, their purity is 1, but they are not positive. Okay, so the mathematical trick, the mathematical, not a trick, but I mean the proof technique we will use here is based on the fact that that ball is not just the ball identified by pure states, but also the minimum volume ellipsoid containing the state space. Okay, so this is some state space. I don't know, I don't mean to represent the quantum one because that would be difficult, but you know, the squid. Okay, so I'm saying that the unit ball identified by pure states is also the minimum. This is not a trivial fact, I will prove it later, but it's also the minimum volume closing ellipsoid for that state space, for that set of admissible states. Okay, this is, and why do I use this formalism? Well, I don't need positivity. Like I said, my measurements are actually quasi-measurements, so they lead to probabilities that sum up to 1, but not necessarily positive. So I don't need the feature that comes easy with the Hilbert space formalism. I will need other features that are very natural in the geometrical formalism. That's why. Plus, of course, we get for free some generality, because what I'm going to say holds in any GPTs, not just quantum theory. Okay, so this is the setup. To the left, in many of my drawings, I will use these geometrical drawings a lot. We have the space of states. So the vertical vector is the unit effect, the identity in quantum theory. There is the hyperplane of states. It's an hyperplane orthogonal to it because, by definition, that effect has probability 1 on any state, and the Born rule has to be an inner product because of bilinearity. That B, double B, is the ball of pure states. So there might be elements on it, points on it, that are not actually states. Okay? But it contains all extremal states. So in the qubit case, of course, it coincides with the space of admissible states. A measurement, M, is a map satisfying that condition written under the horizontal arrow that I explained before, like this one, from the state space to the space of probability distribution. So this would be a measurement, say, from a real qubit, a ball, a two-dimensional ball, a measurement with 3 outcomes like this one, because it maps things on the simplex of the two-dimensional simplex of probability. So this is a 3 simplex, not 3 vertices. So you can see them 1, 0, 0 and permutations. Okay, so this is this duality between the space of states and the space of effects. So in our setup, we are given correlations in this form. So conditional probability distribution of outcomes given buttons that have been pressed. Or equivalently, for each button, we have a probability distribution on the outcomes of this measurement. So we have a set of probability distributions. And we regard them as, we regard this setup as prepare and measure setup. So there are some states associated with these buttons, and there is a P of M associated with this, but we don't assume anything more than that. We require consistency. So the measurement that you are going to infer must contain in its probability range the observation that we have made. So in other words, there must exist states for which that measurement that we infer produces what we have seen. That is consistency. And of course, like I said, if you are interested in, if you use consistency alone, then you have to go to a bipartite setup like self-testing, Bell violations, in order to be able to single out a single measurement. That's not what we want to do. We want to stick to this prepare and measure setup. So consistency alone does not single out a unique measurement. So there are many measurements that are consistent with what we have seen. So what do we do? Well, like I mentioned before, one thing you could think of, you probably will have thought of, is tomography. So if you make some assumptions on the states that were prepared by this state preparator, you can reconstruct the measurement just by linear inversion. The problem is that in order to do that, you would need the states, and So to get the states, you would need to do state tomography, for which you would need to assume a measurement, and so on and so forth. Back and forth, it's a never-ending chain of tomographic reconstructions. So that's not the way we want to go. That's why we say here in red that tomography cannot bootstrap itself. Tomography of these require knowledge of that, tomography of that require knowledge of this. Okay, so what do we want to do is some sort of inference. So let me, one way of justifying this inference is as follows. So say that to the left we have the state space. The grayed out area is the state space. And I have drawn this, let's say it's a ball, but it could be any convex set, doesn't matter. For simplicity, I've drawn here as a ball, so it could be a real qubit if you take this image very seriously. I've drawn unit density, uniform density function on it. So we are assuming that the states are uniformly selected, okay? So we have a measurement that arrow represents a measurement. Like before, the space to the right is the space of probabilities. Those dots are probability distributions, one for each state that was fed into the measurement. And those dots are the observations that we have. The two cylinders to the right represent two different measurements. So a measurement is a linear transformation from the left to the right. So it transforms the state space and the probability density defined on it into another cylinder, because it's a linear transformation. Also maps uniform things into uniform density functions. Okay, so those two cylinders are two different measurements whose probability range is actually the base of those cylinders, and both are consistent with the observations, because both grayed out areas to the right contain the observations that we have. So we have two measurements that map the state space into some set of probabilities, actually two sets of probabilities, we have two measurements, and both are consistent. However, the volume is preserved. So the measurement the one with the basis, the probability range with minimum volume, has higher probability density associated to it, and the other way around for the other one. So we can define a likelihood for an observation. P is a set of probability distributions, so that P calligraphic over there is that set of points given a measurement. And what is this? Well, we have a factor of given by the volume of the probability range. So this quantifies how is the volume to the left transformed into the volume to the right? Is it made bigger or smaller or whatever? And it's in the denominator because the height of the cylinder is inversely proportional to this volume. I called it volume, actually in this figure it would be an area, but okay. So that takes into account the transition from the left to the right. And so with that we move to the left, and then the probability density is what I said, so it's uniform on the state space. So we have a delta function on the state space, and well, this probability of the states that in the next slide I will take to be uniform. So the likelihood of having observations P, that set of probability distributions, given a particular measurement, is given by this formula. You can take this out because we are assuming uniform probability distribution. Okay, so the important elements are, you have a delta function that requires consistency, basically. The POVM was able to produce your observations for some states, and you have the volume factor that comes from the fact that the linear transformation shrinks or made bigger your state space. Okay, now let us make some assumption, like I said. So assume that the states are independently and identically distributed according to a uniform probability density. Not only independent among themselves, but also independently from the measurement. So we are assuming this and that to be IID and uniform. And observe also that the volume of the probability range of a matrix, a linear transformation measurement, is actually given by the determinant of the linear transformation. So what? So our likelihood can be written that way. And if we want to do maximum likelihood estimation, that's it. If we want to go the Bayes way and call this Bayesian inference, we need also to assume, we don't want the likelihood, we want the posterior. So we need to assume a prior on the measurement. And, well, again, we assume uniform prior on the measurement. This is, technically speaking, improper because the set of measurement is not bounded because I relaxed the positivity constraint. So, but anyways, what I'm saying is just we take the uniform prior, which also means the likelihood coincides with the posterior, a la Bayes. And now we take the maximum over the posterior. So we take the argmax over any measurement. This means measurements on d squared equal to L dimensional Hilbert space with n outcomes. And this is the condition that they are measurements of these posterior, and can be rewritten this way. So the delta function becomes a constraint. So it's a constraint optimization, and the determinant gets there. I flipped it, so the arg mean and the determinant goes to the numerator. So what I want to say is this. We can define inferential problem. You can see this either as maximum likelihood estimation with an IID and uniformity assumption here, or as a Bayesian inference with the additional assumption that also this is sampled uniformly. Also measurements are sampled uniform. And if you do that, you get to this optimization problem. So let me spend 2 words. We call this optimization problem data-driven inference. So the constraint that the delta function, the constraint that the probability range of the measurement includes the observations is what we call consistency. I already called that way a few slides ago. And then there is this volume. We want the measurement with a minimum volume probability range that explains what we have seen. We call this, like here we are kind of using some notation from James also, like we are kind of thinking about also James' Max entropy principle. So we call that committal degree of the measurement. So that quantifies basically, we want the measurement that explains what we have seen and as little else as possible. That is the result, the interpretation, the direct interpretation of this inferential, a la Bayes inferential approach. And what is crucial here is that to do inference of measurements, we do not assume state. So this is very different from tomography. We just look at the observed data, the correlations, and we apply a minimality principle, okay? Which can be framed as maximum likelihood, maximum posterior, minimal committal degree. They are all equivalent under some IID and uniformity assumptions. Okay, so data-driven inference can bootstrap tomography. So at some point to associate a model to your devices, you need to break the tomographic, never-ending tomographic chain. This is one way of doing it. Okay, so formal definition. That set over there is the set of consistent measurements for a set of observations P. So we require them, well, to be measurements, so n outcomes measurements, so represented as matrices, real matrices in n times L. And the first condition is the fact that they are measurements, and the second condition is consistency. Okay, so these are measurements, all the measurements that contain in their probability range what we have observed, the set P of probability distributions that we have observed. I take questions at any time, so I'm very happy to, if you have questions, please feel free to interrupt me. I should have said this earlier. And we define, based on the previous slides, the data-driven inference as this minimization over here. So it's exactly what you have seen in the previous slide. Can be seen as maximum likelihood, with some additional assumption, maximum posterior a la Bayes, or minimal committal degree of a measurement. We want to explain what we have seen, and as little else as possible. Okay, this is the end of the first part of my talk. So here I've defined the problem, and so if there are questions, maybe this about the definition of the problem. Now I'm going to solve this optimization problem. Please.
Just, as Bayesian, ultimately I'm going to be allergic to assuming this uniform prior. Do you have any way to extend beyond that?
Well, the problem can be formulated with any prior. Just don't have a clue how to solve it analytically. So for what I'm about to solve this. So I need very symmetric, isotropic, and whatever setup. So yeah, you're right. The problem can be, sorry?
For an analytic solution, I guess.
Yeah, probably you would have to give up the idea of having an analytical solution, I guess, but you can definitely define it with any prior. I mean, here you can assume any prior M, even priors on the states, and so on.
A quick question. So
yeah,
just for the setup. So you're assuming we don't know anything about the measurements, but you kind of know something about the preparations here. The set of possible P's. Is that something you assume? I'm just thinking about the kind of operational setup that I should have in mind for the rest of the talk.
No, actually, the only assumption we have is on the Hilbert space dimension. But we don't assume the states. Otherwise, we could do tomography. We would not need. So the set P stands for probability distributions. These are the probability distributions that I observe over the outcomes of the measurement for any button I press. So I go in a lab, I press this button 1,000 times, and I record the probability distribution here. And then I do again for this and for that.
Oh, okay. Great, thanks.
Thanks to you. Thank you for your question. So this is a very important point. So both here and here we have question marks. Only the dimension of the Hilbert spaces. We could also do inference on different Hilbert spaces dimensions. So like first inference on parameters and then inference on the model. But okay, for now we fix the Hilbert space. So basically the playground is fixed and just we have to adjust just the mathematical description. Okay, so now we have an optimization problem. And we are going to solve this. And like John mentioned, I mean, this is in a particular setup in which we have many nice features like uniformity and so on that allows us for an analytical solution. So to solve this, I need to introduce a couple of concepts. So a tight frame in this geometrical space is just a probability distribution over states such that the tensor product 2 is up to a constant, the identity. Okay, this is just a probability distribution over states, sufficiently irregular, let's say. And then I define another concept. This is instead is specific of quantum theory because it applies to the Hilbert space formalism, that is that of designs. A 2 design, we'll need 2 designs. A 2 design is probability distribution over states such that if I give you 2 copies of states sampled with that probability distribution, you are unable to tell me as a source of states apart from the uniform distribution. Okay, so spherical designs have a very operational interpretation in quantum theory, and it's very easy to see that designs are tight frames. Designs in the Hilbert space sense are tight frames in the geometrical sense written over there. And why do we need that? Because of this theorem. So this theorem solves the optimization problem we had before. The solution is in closed form for qubits, and it's only partial for dimensions higher than 2. What do we mean with that? The arg mean that I showed you in a couple of slides gives us a set. Of course, the measurement that attains the arg mean does not need to be unique. We can, for dimensions higher than 2, we can characterize only a subset of it. This subset is non-empty as long as that dimension, in that dimension there exists a design. So for example, if you are considering measurements with L outcomes, the only designs are regular simplices, so 6, and our characterization is non-trivial if 6 exists in any dimension, in that sense. Okay, so the characterization goes as follows. So you have your observations P, you treat them as if they had been generated by a design, you do linear inversion, and you find a measurement. And the theorem guarantees you that that measurement is minimal in volume, so it attains that maximum. It's optimal in the maximum likelihood, maximum bias posterior, minimal committal degree, whatever sense. Okay, so you can optimize that. You can solve that problem by just a linear inversion. Okay, you have some observation. I say this again because this is the core point. You have some observations. You treat them as if they had been generated, as if here there was a spherical design. You have no idea what was in here, but pretend that there was a spherical design. You do the linear inversion, the same you would do in basic tomography, okay? And you get a measurement, okay? Because of the fact that you used a spherical design, you are guaranteed that the measurement you get is optimal in this inferential sense, okay? A couple of comments. So this is a complete characterization for qubits because the state space is a ball, and it's a characterization of a subset of that arg mean for dimensions higher than 2, because this theorem internally uses an outer approximation of the state space in terms of that ball that I mentioned earlier, and this approximation is exactly an approximation, not exact, for any dimension higher than 2. So in that case, you lose one of the two directions of the logical implication. And then the example I mentioned earlier, so if the measurement has exactly the right number of outcomes to be informationally complete but not over complete, so d squared, L outcomes, then the only regular simplex is, the only two design is the regular simplex. So this characterization in that sense is in closed form, because otherwise you would need to look for probability distributions such that you have a design, and so you could say, okay, but your characterization just moved the problem from finding the measurement to the problem of finding the probability, such that we have a design. That is partially true, but at least for informationally but complete but not over complete measurement, this problem does not arise. Okay, this is the main result. Again, if you have any question, I'm almost done. So probably I'm running out of time. So if you have any question, they are very welcome. I still have a couple of those, sorry. I think I still have 15 minutes.
Let's give you, let's say 10 minutes.
Okay, thank you. So why designs? So one important point that comes out of this. So our original idea was we have this inference, let's frame it, let's define it formally, and let's solve it. But then after that, we realized, okay, designs plays an important role here, a uniquely important role. So this role, like I mentioned maybe before, is due to the fact that if you have a design like the one to the left, the square is a design. I could have drawn also the regular triangle, not the regular simplex, it doesn't matter, just harder to draw. Its minimum volume enclosing the ellipsoid is the unit ball. While if you have these can be seen as points on a real qubit, here, 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 and here. This is the block circle. Their minimum volume enclosing ellipsoid is not the block ball, it's something like that. So, and this is the case even though rectangles are informationally complete. So rectangles cannot be used here, informationally complete, but not design structure cannot be used here if you want your measurement to be maximizing the likelihood or the posterior and so on. So this is the point. Designs emerge naturally as soon as you consider the Bayesian inference of devices as the only mathematical tool that allows you to solve the problem of the inference. Okay? Okay, so this is kind of an intuition. I don't go into the proof of the theorem, but the theorem uses Jon-Fritz theory on minimum volume enclosing ellipsoid. It's a result in differential geometry that was derived in the 40s, I think. Okay, just one comment. I mentioned at the beginning that the inference that we do on measurements can be done also on states. It's just more difficult. And why is it so? Well, now maybe we have the ingredients to understand why it is so. Our inference of measurement measurement relied on an outer approximation of the state space that can be done nicely with a ball, because pure states live on a ball, so the state space in some sense is not that different from a ball. The effect space is much harder to characterize. It's a bicone, no? The cone of operators that are in between 0 and the identity. And it turns out that you can approximate it with what we could call D cone, D being the dimension of the Hilbert space. There are D, like this is the setup for 2 qubits, a 4-dimensional Hilbert space. So the one for the qubit would be trivial, that would be the bicone. For the Q-trit, it would be like this. And that is for the Q-quart. And what do those circles, those balls represent? They are balls on the plane of trace 1, trace 2, and trace 3 operators. And the ball is given by, again, by a constraint on the purity. And you can do inference of states in the same way. So you must assume that your observations have been generated by a measurement that supports a design on those balls. I won't go into details, but I think you can probably see the logic and the analogy with what we have seen before. Those designs, by the way, are called scalable frames. Scalable because you allow for a probability distribution that scales them. Okay, so this is the dual problem of inferring the states, just mathematically more complicated. We can solve it. Okay, so conclusion. The idea here is that we want to do inference of states and measurements. We want to be able to attach mathematical description based on observations only. That's why we call this data-driven. And in doing so, in solving this problem, we find out that the mathematical tool that you really need are designs. In particular, in the lowest, the case with minimum number of elements, it's 6. And this shows, in our opinion, the import, the relevance, the natural emergence of designs in this inferential problem. So I know that designs play an important role, SICs in particular, an important role in other contexts, in other interpretations, probably will be discussed later. And this allows us to do things such as bootstrapping tomography. So attaching a meaning to a device without assumptions on any other device. Just a few references. So I mentioned that technically our results are based on ion theory on minimum volume closing ellipsoid, first paper. Something I forgot to mention is the following. So we look for the measurement with the smallest probability range. Its Euclidean volume must be minimal, so we want to explain what we have seen and as little else as possible. This is, there is a nice analogy here. So Blackwell proved that for the classical case, the range inclusion implies the existence of a map, physical map, mapping one measurement into the other. So a measurement whose probability range is included in the range of another measurement can actually be simulated by the strongest measurement. So there is this hierarchy, of course, it's a partial order. There is this hierarchy in the classical case. This is Blackwell. Alberti Ullmann showed that this is also the case in quantum theory, but only for dimension 2. I mean, this actually, it's not what they prove, but immediately follows from them, from their work. So this idea of minimizing the volume has also a very strong operational interpretation that is typically used in like resource theories and contexts in which, statistical sufficiency is relevant. So the problem of simulating one device, when one device can simulate another one. Then there is that work of ours where we introduced these ideas a few years ago. And then recently, Anna Shimusiak with collaborators has been working a lot on related problem that relates to what we have done. So morphophoric POVMs, just quickly I can mention that they are measurements such that the state space is mapped into something that has the same shape as the original state space, not deformed, like the name suggests, and the relations of that with cubism that we will hear about in a moment, I think. And the results I presented here are mostly in this recent work over there that is only on the archive for now. This is really, so thank you very much. Thanks a lot.
Okay, thank you so much for this great talk. Questions?
Please.
Thank you. So thanks for the nice talk. I'm curious how this relates to this other notion of, it's called theory agnostic tomography or so. I think it's by Rob Speckens and Kevin Resch. They also say, suppose I have preparations and measurements that I don't understand, and I want to fit basically a probabilistic theory to it. Then they collect data in a similar way as you do, and then from the data they try to infer and fit to it some state space, some effect space. So I wonder if that's actually related, or more like what the difference is in this scenario that you're describing. Perhaps it seems like maybe you go to it anyway, but it seems to me like maybe if less measurements, because they're really trying to probe like lots of measurements, lots of preparations, but it seems like in this box picture at least, you typically have few of them.
Okay, here there is a single measurement, single POVM. It typically has to be informationally complete because we want the probabilities generated to be full dimensional body. Otherwise, we have like non-invertibility problems. That's a problem. I think so. To try to answer your question, I think they are more interested in reconstructing the structure of the admissible set of states and the admissible set of effects. While we assume the dimension of the Hilbert space, or even if we are in an arbitrary GPT, we assume a given set of admissible state to be given. And what we want to do is to actually reconstruct the device that was in here. So I would say probably the difference is that we assume the model and we do inference of the parameters. And all of them in the sense we reconstruct the POVM. They are, if I understand correctly, more interested in inferring the model itself. I think what you do can, at least to some extent, be generalized to that level. So like we assume the Hilbert space dimension, we may not assume that and consider, different Hilbert space dimensions, and some measurements in there would be favored and others would be not favored by this inferential argument over here. So some of them would better fit the data, so would be their cylinder would be higher, the probability density associated with them would be higher, and so we would favor them and so on. So I think probably this can be extended to inferring the model itself. Thank you very much for your question.
Thanks. This is just maybe a long shot, but I'm just curious, following up on my question in the middle of your talk, whether you think maybe that weighted two designs are going to be relevant in the case where you don't have a uniform prior.
Actually, we already have, so here, I didn't call them weighted, but they are actually weighted because they are a probability distribution over states. Okay. So that P over the paragraph in between, that P is the weight.
The weighted two designs solve the same problem.
So weighted two designs solve this problem. Okay. So I have really no idea how to go about solving I haven't thought about it, the more general case. I don't have a good feeling. I don't think it can be analytically solved for situations that are more general than IID and uniform, but I would be happy to be proven wrong. So they are also called scalable frames, the ones above, exactly because of this. Scalable there means the same as weighted in the context of designs. So thank you very much for your question.
Okay, we have time for a couple more questions.
Okay, so if there are no more questions, let's thank again our speaker.
Thank you.